Hello, and welcome to Understanding Digital Fuel Injection. The purpose of this video disc is to present the digital fuel injection system in a unique, straightforward manner. As the title implies, everyone viewing this presentation should have an understanding of digital fuel injection after the conclusion of this program. The format of this presentation is changed somewhat from previous programs in that the accompanying summary book has become a comprehensive study guide with self-administered quizzes and exams that will enable you to check your retention and understanding of the information presented. The video disc will stop at two separate places to give you time to review material, check your retention, and, if needed, provide the opportunity to repeat specific sections of the presentation. It will be your responsibility to restart the program after these stops. We strongly urge that you follow this program's format as closely as possible in order to obtain the maximum information impact possible. Read the summary book carefully before viewing the video disc. Do not skim the material or attempt to absorb it all at once. Take a break at the stops. Take time to thoroughly review the material. Be sure you understand it. Discuss it with other viewers. Ask questions. There are a lot of details to cover, and all of them are important. So, without any further delay, let's begin with a definition of the system's name itself. First of all, the term digital refers to the on-off form of electrical signals the system uses to monitor and calculate the necessary engine fuel supply. Also, the fuel necessary to maintain engine operation through all driving conditions is injected into the engine. When these terms are combined, we get the name digital fuel injection. Basically, the DFI system operates as follows. Using input signals from the sensors and switches, the electronic control module, ECM, calculates the amount of fuel necessary and, in turn, activates the throttle body mounted fuel injectors. When specific operating requirements are met, the ECM monitors the oxygen content of the exhaust gases by means of an exhaust sensor and makes corrections to achieve the ideal air-fuel mixture of 14.7 to 1, the ratio at which the catalytic converter can most efficiently convert the hydrocarbons, carbon monoxide, and oxides of nitrogen pollutants in the exhaust to inert gases. When the oxygen sensor is active, this is known as the closed-loop mode of operation. The sensors and switches provide data to enable the ECM to provide an acceptable level of drivability for all engine operating conditions. The DFI closed-loop system can be most easily understood if it is separated into a number of subsystems. Then, as each subsystem is defined, its role in the total DFI systems operation will be more easily understood. We will be presenting the first 7 subsystems in detail, utilizing the summary book that accompanies this release, as we have already indicated. The first subsystem is the fuel delivery system, the purpose of which is to provide fuel at the correct pressure and quantity for metering by the injectors. These specific components of the fuel delivery system are the fuel tank, fuel pump, fuel delivery line, inline fuel filter, fuel pressure regulator, and 2 fuel injectors in the throttle body, and fuel return line. In operation, fuel is delivered from the specially designed fuel tank by a twin-turbine electric pump that is integral with the tank float unit. The fuel passes through a filter assembly mounted near the left rear wheelhouse, which has an element capable of trapping particles smaller than 1/3 the size of a human hair. Next, the fuel travels to the fuel metering body, where a constant fuel pressure is maintained by the integral regulator assembly. The 2 electronically activated fuel injectors will then deliver the fuel into the throttle body above the throttle blades. To complete the cycle, any excess fuel is returned through the fuel return line to the reservoir within the fuel tank. The purpose of the next subsystem, the air induction system, is to control and distribute the air necessary for combustion to take place within the engine. The first of the 3 components that accomplish this purpose is the throttle body, which is located under the fuel metering assembly. The throttle body contains 2 bores, each of which has a throttle blade mounted to a common shaft, which is in turn connected to the accelerator pedal. The amount of opening by the throttle blades is a factor in determining the engine speed. Engine idle speed is controlled by the second component of the air induction system, the idle speed control actuator. The third component is the intake manifold, by which air is distributed to each cylinder. This manifold is an aluminum single-plane design, engineered especially for DFI engines with modulated displacement. That covers the DFI fuel delivery and air induction system components. The next subsystem, Engine Data Sensors, provides the DFI system with the necessary information for the fuel management portion of its operation. The DFI system establishes the base amount of fuel to be delivered into the engine, depending on the factors of engine speed and air density. The system is therefore known as a speed density fuel management system. The factor of engine speed is determined by engine revolutions per minute, RPM. The engine speed signal originates from the 7-terminal HEI module in the distributor. Pulses from the distributor are sent to the ECM, where the time between these pulses is used to calculate engine speed. The air density factor, or amount of air within the intake manifold, is determined by the variables of manifold air temperature and engine manifold absolute pressure. These two signals come from the manifold air temperature sensor, MAT, which measures the temperature of the air-fuel mixture in the intake manifold, and the manifold absolute pressure sensor, MAP, which monitors changes in intake manifold pressure, which result from engine load and speed changes. Using information from these inputs, the base fuel delivery calculation is made. As operating conditions change, the fuel ratio is then modified by information received from various other data sensors. The list also includes a number of switches which have an effect on other subsystems, such as idle speed control, electronic spark timing, and modulated displacement. These other sensors and switches include throttle position sensor, TPS, coolant temperature sensor, CTS, barometric pressure sensor, BARO, vehicle speed sensor, oxygen sensor, ignition switch, crank signal, brake switch, drive switch, reverse switch, third gear switch, air conditioning switch, cruise control switch, and the throttle switch. The chart found on page 9 of the summary book summarizes input signal usage. It can be used as a reference to determine which signals are used by which system. A most important point to remember in understanding digital fuel injection is that the engine speed signal, intake manifold air temperature, and absolute pressure signals are used to calculate the base amount of fuel to be delivered. The remaining sensors only affect a correction to the base calculation. Now, turn to page 7 of your summary book, where you will find review exam number 1. Take the exam, marking your answers in the summary book. Make use of the information on pages 1 through 7 to assist you. Only after you have a solid understanding of the material should you restart the disc. If you want to review sections of the disc, consult the contents on the disc cover for the location of specific subjects. Now let's turn to the next DFI subsystem, the electronic control module, referred to as the ECM. This component is at the core of the DFI system. It is responsible for monitoring and controlling all of the DFI system functions. The brain of the ECM is called the Central Processing Unit. The CPU monitors engine temperature, manifold pressure, and a host of other parameters by using the signals from various data sensors. The CPU can also send signals to a variety of actuators, such as the idle speed motor, distributor, and fuel injectors, as well as inform the customer and mechanic of possible trouble in the system. To talk to the engine sensors and actuators, the ECM needs an input-output device. The CPU uses this device not only to transmit and receive, but also to convert variable inputs into digital on-off signals. Before the CPU can receive or send information, it must follow instructions Cadillac engineers have written for it. These instructions are stored in memory. There are 3 types of memory. Read-only memory, ROM, which is the program that includes the overall control of the DFI system. This program, written by Cadillac Engineering, cannot be changed and can only be read from memory. If battery voltage is lost, instructions in ROM will be retained. Random access memory, RAM, is what is called the scratch pad memory for the CPU. Information can be read into or out of RAM, such as engine sensor information, diagnostic codes, and DFI operation calculations. These are stored in RAM temporarily, so if battery voltage is lost, all the information in RAM is lost. Programmable read-only memory, PROM, contains specific engine calibration data for each emission system and transmission. This memory device is programmed by Cadillac Engineering, and its information is retained permanently. There are two serviceable PROMs in the ECM. The ECM uses the information from the various sensors to make calculations and issue output commands. The most important output command is directed to the fuel injectors. Each injector must open at the correct time and remain open for the desired length of time for the engine to operate properly. There are two patterns of injector output command: synchronous and asynchronous. Synchronous commands are issued under most conditions, with one injector command pulse issued for each distributor reference pulse, and the injectors being alternately activated. Asynchronous commands are issued under the condition of deceleration at closed or nearly closed throttle, when the injector on time is extremely short, with one injector command pulse for one or more reference pulses. In other words, one injector pulse for every distributor reference pulse is not necessary to maintain performance and drivability. The length of time the injector remains open is known as pulse width. Pulse width is based on the following factors: manifold pressure, volumetric efficiency, manifold air temperature, fuel pump voltage, barometric pressure, number of cylinders, commanded air-fuel ratio, closed-loop control, EGR correction. Although all of these factors make up the final determinant of pulse width, we will discuss only the four highlighted here. The first is manifold absolute pressure, which closely represents engine load. At idle, when manifold pressure is lowest, less fuel is required by the engine. As engine speed increases, manifold pressure then rises, which signals the need for increased fuel to overcome the additional load on the engine. The pulse width is increased as manifold pressure increases. This is typical of what happens when a car accelerates. To facilitate understanding of this concept, the pulse width has been lengthened and the interval between injections lengthened. On an actual engine, it appears as a constant spray of fuel. The volumetric efficiency is the measure of the engine's ability to draw in or intake air for use in combustion. By definition, it is the ratio of the actual volume of air in a cylinder compared to the maximum volume that could enter a cylinder under ideal conditions. When the efficiency is high, the pulse width is lengthened since more air, or let's say air at a higher density, is available for combustion. Volumetric efficiency is based on manifold pressure, engine speed, and the number of cylinders in operation. Let's look at just engine speed to gain a better understanding of volumetric efficiency. At lower engine speeds, the efficiency is higher because more time is available for air to enter a cylinder. As we see here, sufficient time is available for the cylinder to completely fill with air, which indicates a volumetric efficiency of 1. At higher engine speeds, the intake valve closes before the cylinder is completely filled, leaving a small dead space. The speed of the air entering has increased, but not fast enough to allow the cylinder to completely fill, which results in an efficiency of less than 1. When this occurs, less fuel is needed to maintain a constant air-fuel ratio, so the pulse width is shortened. This is an oversimplified explanation of one aspect of volumetric efficiency, but it should provide some insight into its effect on pulse width. The air temperature in the intake manifold affects both the density of the incoming air as well as the ability of the fuel to vaporize when it contacts the air. When the manifold air temperature is low, the density of the incoming air will be higher, resulting in a higher oxygen content. And also, the rate of fuel vaporization will be less. For these two reasons, the pulse width is increased. At higher manifold temperatures, the pulse width is shortened to reflect the change in fuel vaporization and air density. The commanded air-fuel ratio is affected by coolant temperature, as well as changes in engine load. At low coolant temperatures, additional fuel is provided during engine cranking and warm-up. This acts similar to the choke system on a carbureted engine. At higher coolant temperatures, when less fuel is needed, the pulse width is shortened. Increased power for acceleration requires an increased pulse width. When the throttle is at or near wide open throttle, the pressure in the intake manifold increases to near atmospheric. This information is sent to the ECM, which lengthens the pulse width appropriately. We have said that the DFI system is a closed-loop fuel management system. That is true, but the system operates in what is referred to as open loop during periods of rich engine operation, such as startup, warm-up, power enrichment, wide open throttle, and when diagnostic codes 13, 44, and 45 are set. While in open loop operation, the ECM determines pulse width on the input from the various DFI engine sensors, but ignores the feedback from the oxygen sensor, since its input during rich engine operation would incorrectly adjust the air-fuel mixture. Take time now to review the ECM, pulse width, injector operation, open loop operation, and closed loop operation, pages 10 through 15 in your summary book. And take review quiz number 2 on page 15. Follow the review procedures already established if you have problems understanding or retaining any of the information. Now we turn to two very important DFI subsystems: idle speed control, ISC, and electronic spark timing, EST. The purpose of idle speed control is to precisely control engine idle speed whenever the vehicle operator allows closed throttle operation. This is accomplished by means of the ISC actuator, a reversible DC motor-driven throttle control. This unit, mounted directly on the throttle body, acts as an idle or throttle stop to regulate throttle angle. Using various DFI system inputs, the ECM controls engine idle speed to maintain a desired RPM and also control emissions based on engine loads and vehicle operating conditions. The ECM issues output commands to the ISC motor, causing the plunger to extend or retract. This increases or decreases the throttle angle, the amount the throttle is open, thus controlling engine speed. Idle speed control is required during 3 engine operating conditions: crank and start up, idle, deceleration. Let's discuss each situation separately. During engine cranking and startup, a slight throttle opening is required. Since operator action is not required, the ECM commands the ISC plunger to slightly extend, thus allowing sufficient air to enter for starting. When the engine has started and is running at idle with low coolant temperatures, the ISC plunger extends to provide increased throttle opening, increasing engine speed during warm-up. This functions like a fast idle cam on a carbureted engine. Also at idle, the ISC provides increased throttle opening to compensate for changes in engine load, allowing for a more consistent idle speed. The last function of ISC control is to provide a partial throttle opening during deceleration to prevent engine stalling and control emissions. This feature acts similar to a dashpot used on some carbureted engines. The electronic spark timing, EST system, provides precise control of spark advance to provide maximum vehicle performance, fuel economy, and exhaust emission control. The system consists of a redesigned high-energy ignition distributor, the DFI ECM, and various DFI system sensors to regulate spark advance during all operating modes. During cranking, the ECM signals the distributor to ignore spark advance signals and maintain timing at a fixed 10 degrees. Once the engine is running, the distributor begins accepting spark advance signals and begins varying spark timing based on engine speed, manifold pressure, coolant temperature, and barometric pressure. Since we have reviewed the various DFI sensors, switches, and engine systems, the next step is to gather all this information together and look at it in terms of actual vehicle operation. We'll do this by discussing what occurs during these 8 specific operating modes: ignition off and on, engine cranking, idle, off idle, tip-in enrichment, part throttle, acceleration, power enrichment or wide open throttle, deceleration. Ignition off and on. When the ignition is off, the ECM is inactive, except for the storage of any malfunction codes that have been set. When the ignition switch is turned to the run position, the ECM initializes or powers up, which energizes the fuel pump. The fuel pump remains on for only 1 second if a crank signal is not received by the ECM. Cranking. When the engine begins cranking, the EST system maintains spark advance at 10 degrees, while the ISC actuator holds the throttle partially open to facilitate starting. When cranking begins, the ECM issues prime fuel pulses to provide an initial fuel charge for starting. The number of prime pulses is dependent upon coolant temperatures, with more pulses being delivered at lower coolant temperatures. When priming, both injectors simultaneously inject fuel at a fixed pulse width of 10 milliseconds. Once these prime pulses have been delivered, the ECM begins alternating fuel pulses with the width or on-time length determined by the numerous factors discussed under pulse width. Idle. Once the engine starts, the ECM begins varying the pulse width, spark timing, and idle speed based on current operating conditions. When the engine is first started, coolant temperature is the primary influence on pulse width, spark timing, and idle speed. The injectors are issued command pulses based on engine speed. The distributor is signaled to accept varying spark advance signals, and the ISC actuator receives commands to regulate idle speed. Off-idle tip-in enrichment. Whenever the throttle is open from idle, a sudden increase in manifold pressure takes place. This sudden increase causes fuel droplets to condense on the manifold walls instead of vaporizing with the incoming air. This results in a lean air-fuel mixture entering into combustion, which can cause the engine to stumble. To smooth this transition from idle to part throttle operation, additional fuel is provided in the form of a tip-in enrichment. As the throttle is open, the injectors begin pulsing simultaneously to provide additional fuel. The pulse width, which is determined by the manifold air temperature, compensates for fuel vapor condensation in the intake manifold. The lower the temperature, the greater the condensation, and thus the longer the pulse width. The injectors are activated alternately once the engine passes through this transition from idle to part throttle operation. Part throttle. The engine primarily operates in the part throttle operating mode. The pulse width, determined by the various DFI inputs to the ECM, is primarily influenced by volumetric efficiency, engine speed, coolant temperature, and the number of cylinders in operation. Spark timing is varying and is primarily based on manifold pressure, engine speed, and coolant temperature. Once the engine enters closed loop or warm engine operation, the influence of coolant temperature on pulse width and spark timing is reduced. Since the driver is in control of the throttle, the ECM issues a command to the ISC actuator, retracting the plunger, preventing interference with throttle operation. When the throttle angle is quickly increased, fuel droplets condense in the intake manifold just as they did during the transition period from idle to part throttle. Additional fuel is supplied by simultaneously pulsing both injectors. The pulse width is dependent upon the rate and amount of throttle opening. Maximum power can be obtained by fully opening the throttle. When this occurs, the manifold pressure rises to near atmospheric. Once the map sensor sends this information to the ECM, it gradually increases the pulse width to the richest value allowed, based on coolant temperature. This enrichment continues until manifold pressure decreases. The last operating mode we'll discuss is deceleration. During deceleration, the engine requires a minimum amount of fuel, just enough to keep the engine running. To reduce fuel consumption, the ECM delivers fuel pulses simultaneously with the time interval between pulses longer than during other operating modes. By increasing the time interval between simultaneous fuel pulses, the length of the pulse width can be increased to a value that can easily be controlled. If alternate fuel pulses were delivered at regular intervals based on engine speed, the pulse width would be so small that it would be difficult to regulate. Also, during deceleration, there is a possibility for the throttle to completely close, resulting in only a small amount of air entering the intake manifold. When this occurs, the engine, which is still operating at a speed above idle, can emit a high amount of exhaust emissions due to this rich air-fuel mixture entering combustion. If the throttle is held partially open, sufficient air can then enter the engine to provide a lean air-fuel mixture. The ISC actuator provides this throttle opening by extending the plunger, partially opening the throttle. Even though specific sensors, switches, and control functions may change, the DFI concept provides the basis for future systems that can provide an efficient air-fuel mixture and emission controls. For this reason, and because electronic designs such as this will continue to play increasingly important roles in Cadillac systems of the future, an understanding of how the system operates is important for all Cadillac personnel and absolutely essential for Cadillac service technicians.